Good morning, everyone. Welcome to the EasyPower Tuesday Refresher. This is Jim Chastain. I'd like to welcome all, and certainly you're welcome to contribute to the discussion, and we'll take questions at the end of the presentation as we have time. So I'll jump right into the topic of the day. Where we're headed with this is essentially talking about the differences in utility applications for the EasyPower tools, and there's been some confusion regarding arc flash and how it should be handled in utilities. So for starters, NFPA 70E Article 90 has several paragraphs including disclaimers where that specific standard does not apply to situations involving utility companies, but still OSHA requires companies to provide a safe work environment against known hazards. And then they jump into a mix with some information specific to single phase arcs and the way it leaves some gray areas about the topic. So I'm going to try to do my best to bring some specificity to how EasyPower applies in all these applications. So we will be talking about how EasyPower deals with open and closed buses up to and beyond 15,000 volts. And then we'll be jumping into single line to ground fault calculations beyond that, all of which are incorporated in EasyPower. Well, there are several models for arc flash. The de facto recommended standard for most systems is the IEEE 1584 model, which was developed in 2002. That was developed by running a bunch of testing on actual arcing events, and then the model was developed by coming up with a best fit equation that met the empirical data. And there's some leeway in terms of variability, and so as far as the results, and that's why both IEEE and NFPA refer to the solutions as estimates because of the variations that were seen in the characteristics of an arc itself. So there's always a tendency to lean towards a worst case situation, which would include some guard banding in terms of personal safety. So the parameters within which the IEEE model is applicable is this matrix right here, and utility companies often have to address situations that lie outside these boundaries. For instance, system voltages may be well above 15K, available bolted fault current may be well above 100,000. The gap between electrodes may exceed 152 millimeters, and then the type of faults, the IEEE model only deals with three-phase faults, and that's not the case in most utilities. This information is available usually in some format within the NFPA 70E document. It kind of changes location and changes content based upon which version you're looking at, and the list has kind of grown and shrunk and kind of changed, which doesn't help things that much. But real briefly, they refer to the Doty-Neal paper as incident energy calculations for three-phase systems 600 volts below between 16,000 and 15,000 amps. The Ralph Lee paper calculates incident energy three-phase arcs in open air systems above 600 volts and becomes more conservative as voltage increases. And then there's the IEEE 1584 standard, which, as we just saw, has brackets and recommended usage between 208 and 15,000 volts, three-phase, both 50 and 60 hertz, 700 amps up to 106,000 amps, and then a limit on the conductor gaps. Back in the 2009 version of NFPA 70E, there was a table included for incident energies for open air single line to ground between 1,000 and 500,000. This table itself is kind of migrated, and so one of the things that this chart calls out are the areas where there's deficiency or concern about using any of these models in specific areas. And so one of the complaints about the Ralph Lee paper is it gets more conservative, which means it requires higher and higher incident energy, which requires more and more PPE, and consequently could make a situation more dangerous if we had to suit up to the level that's required or being suggested. And then this last recommendation is we'll see is a chart that's migrated from NFPA to ANSI IEEE and to NESC articles, and that's again where we're going to go to for the single line to ground applications. So what does EasyPower do with all this information? Well, first of all, when there's a number of different types of buses, and as the voltage changes, the gap, the default gap, will vary on each of these buses, and the gap itself that's used for predicting the arc is different between each of these types of buses, and as the voltage increases, that gap will increase. So that allows us to use the IEEE 1584 model over the full range of voltage, and then by selecting open air, it will make adjustments that are allow us to use that model within the constraints of a three-phase arc flash. Now, additionally, if you'll look in the EasyPower arc flash hazard tab of the short circuits options section, you'll notice that you have four choices. If you select the 1584 model, you'll see that note below suggests that above 15,000 volts, a program uses the Ralph Lee model with some added notations. You also have the ability to select NFPA 70E 2015 D2 and D3. So this will use the combination of Doty-Neal and Ralph Lee based upon what voltage your system's at. So there is that option. These other two models, V6.0 and V7.0, are actually legacy models from the early days of 1584. There are segments of the voltage spectrum where the arc current might be calculated showing higher than the bolted fault current, and so these anomalies in the 1584 model were cause of concern, and some early EasyPower users requested that we modify, and that's where these two equations came from. If you run into a situation where your arcing current seems too high, by all means contact tech support, and they can walk you through if either of these two models are appropriate. So the bottom line as far as EasyPower is that based upon the IEEE model using the four equations, we have the ability to incorporate different variables, and we've kind of talked about these before in other refresher sessions. But these are the variables that get rise to the arc flash hazard options that you find in the tools, and it gives you the ability to have actually the most accurate estimates of three-phase incident energy in the industry. So that's covering three-phase pretty extensively. Now we need to talk about single line to ground, and this is an area that is primarily of a concern in the utility application where you have high tension wires, and because of the distance between the phases, very seldom will you see a phase-to-phase arc, or almost rare is going to be a three-phase arc. And so what we're going to do is kind of come at this backwards. We're going to start off solving a single phase energy, and then have the ability to take some multiple of that to go to line to line and to multiple phases, or to three-phase. Okay, so the way this works in EasyPower, it's pretty straightforward, and that is you set up the bus as an open air bus. You do this in database edit. You make sure that you understand what the voltages are that are being set up for open air, and then in short circuit focus, you designate under the arc flash hazard tab of the short circuit options the desired working distance of the open air worksheet, and I'll show you this in a second. Then you go to Advance, verify that the correct minimum voltage is being applied, and then when you fault the buses, you select the single bus to ground as the fault mode. So this is not something that we've run across in the three-phase modeling before, and so let me jump into the tools and let's kind of walk through this. Once you've done it a couple times, it certainly becomes a lot more understandable. So what I have drawn up is a one-line diagram that gives me the ability to look at several different voltages, and let me kind of show you how we've made this adjustment. All right, so I'm in the EasyPower tools. We have the utility here for 345,000 volts with a 30,000 amp supply. Now I've labeled each of these buses with a specific reason. For instance, I put a 1 second limit on this particular bus fault. Once we connect to a utility, more often than not, we have the ability to receive from the utility a maximum fault trip time, and we can use that when there's no protective device designated. So in some of these buses, I've designated a 1 second maximum calculation. I'll show you how I did that, just to show what the energy is being produced is. And then others, we actually have them protected by relays, and in this case, we're using a 3-cycle breaker opening time plus the delay from the relay, and likewise, and so we have that for different voltages and different current. So let me kind of jump into the details and let's show you how we did this. So for my 345K bus, again, I'm confirming it's 345K. It's set up as an open air bus. Now this one, in my arc flash hazard tab, I'm going to use the maximum designated trip time that the utility's given me. So in this case, I want to use 1 second, and there's reasons for this that I'll talk later about in a minute. So that's set up. When I come down to this bus that I want to have protected by the relay, I've set it up as open air. It's still 345, and under my arc flash hazard tab, it's being auto-calculated by the tool. So what's going to protect it is this relay. And if we look at the relay, it's like any other relay in that we've designated the manufacturer. In this case, it's a multifunction relay. We're showing both phase over current and ground over current. Again, phase to ground is going to fall into one of these categories, and it's going to activate the 3-cycle unit. When I go to the settings for the phase over current, these are the set points that we have for this relay: the tap range, the tap setting, the ratio for the CT, the very inverse curve, and then the time multiplier. All right, and this is set up just like any other relay would be. On my overcurrent to ground, same parameters: my CT ratio, my tap range, my tap setting. In this case, we're going to be looking at set it for 200 amps trip, using a very inverse current curve, and the time multiplier. Now in this case, I read it was set up for 3.5. You notice I don't have 3.5 on my range. So what I did is I just type in 3.5, and the tool accommodates that interpolation. All right, so the bottom line on all of this is that every bus is set up as open air because these are all high tension connections and terminations. I've done the same thing down here. So I have a couple transformers. This one just to drop my voltage from 345 to 34.5. There's nothing special about the way that the transformer is set up. Standard kVA or MVA rating. The impedance we use to calculate. The bus down here, I want to limit it at 1 second, and I compare it against the relay protected 34.5 kV. I've adjusted, so this is a transmission line rather than a cable. It's an ACSR material. The size is a 477 Pelican. The length is in miles. The mean distance between phases is by default. I can adjust it if I want to, and the height can be adjusted, but these are the standard values. And then once I've calculated the impedance, the tool does the rest. So I've got two different buses here. One set up, the length of the cable is set up, or the transmission line set up to give me a 5,000 amp, and then the transmission line here is set up to give me a 3,000 amp. Again, I want to see what the impedance, what the trip time is, and instant energy predicted if it's protected by the relay. Okay. Same thing over here. The only reason that I'm interconnecting these two is so I can have everything on the same one line. Without this, I'd have an isolated utility connection, but by leaving this high voltage breaker open, it allows me to have both utilities and gives me multiple voltages on the same one line. Okay, so all that seems pretty straightforward. We're going to go to short circuit focus. Okay, so the trick is in the short circuit options, arc flash hazard tab. All right, I want to designate and apply working distance for open air, which will vary based upon the voltage and that chart we were looking at. We're going to go down here and look at advanced. We're going to select apply to open air buses, which will calculate based upon the NFPA reference that we saw earlier. And I want to apply the minimum kilovolts to be above 15 kV. Now, you'll see later we have the ability, the tool applies for three-phase a multiplier and for a line-to-line a multiplier, but what we're doing initially is predicting the instant energy for a single line-to-ground fault. All right, so we're good with all this. We're going to apply all of this. We're going to go back and pick out a line-to-ground fault and fault the buses, and as we do that, it gives us instant energy predictions. All right, so here we have an arc flash boundary, instant energy, and the working distance. And again, the working distance is part of the chart that's being recommended by the OSHA document. Now all the results will be the same as far as how we can look at them in the arc flash hazard report. But you can see where I've set up a time delay for a bus limit. I don't have the specificity or the details on that particular calculation, but any place I have the relay doing its function, we can see both the overcurrent results and the ground results for that particular bus. So, and this will vary based upon where I have my grounds in the system. So that's how it's done. If we go back here and say, all right, so I'm good with all that, what would it be if I had a line-to-line? This is where it applies the multipliers, and so as we change that fault type, it will make the adjustments for the line-to-line fault, and then when we go to the three-phase fault, it'll do the same thing, make an adjustment there. Okay, now I want to take the rest of the time, so if there's any questions on this, we'll handle them at the end of the session. What I want to take next is to kind of go into what all this is based upon. So let me kind of go back to my PowerPoint and slide on down. If you look at OSHA 29 CFR 1910-269 Appendix E, you'll find this discussion where they give us several tables and they're talking about selecting reasonable incident energy calculation method. And specifically, they're comparing a single phase. You notice there's single phase, three phase in a box for different voltage ranges. On the left, we have a choice of different calculation modules, and on the right is a recommendation of the where to apply these methods. So off the bat, you can see we have a new player in the form of ArcPro, but you notice it's not recommended for any three-phase applications at low voltages. Now, I have nothing to say about this product. It's what I've seen of it, it's a DOS-based analytical tool that will calculate heat flux, which, if you look at this, I guess it's on my next chart, you still need to be able to predict the trip time, which you cannot do with the tool. And so you'll need EasyPower to be able to calculate the trip time of a breaker or a relay, and to be able to use the data. Then secondarily, you'll notice that even on a single phase greater than 15,000 volt application, that there's some notations here. And if we look at why they don't recommend the IEEE approach, or actually any of the equations, it's because they're too conservative. And again, that means they'll calculate incident energy higher than what's necessary, more because they're being on the safe side or the conservative side of the curve. So you might ask, well, so if you look at this, we go what they recommend to apply the ArcPro. They say, well, OSHA Health Administration has deemed the results of this method reasonable when you adjust them for the three-phase arcs. So what they're saying is use the energies that the tool calculates and then adjust the calculation method for three-phase and three-phase in a box. So it's just kind of backwards from the way EasyPower has done things. We have the ability to predict three-phase in a box, but we're too conservative at the higher voltage and incident level. So you might say, what happens, or how do we go to the model I just gave you? Well, as I mentioned earlier, this started out as a tab or a table in NFPA 70E 2009, and it was labeled as a heat flux rate, which is calories per square centimeter per second. And if you'll notice in the fine print, these were derived from a commonly available computer software program. Other methods available are for exposed values may yield slightly different but equally acceptable results. Okay, so this is where we're stepping up and saying, okay, I tell you what, we can take the variables that we have in the database and literally come up with the calculations that will curve fit all these data points for the voltages and the current that are being listed. And since the tool already has, EasyPower already has the trip times in the adjustment, we can produce the incident energy. And so even though this particular chart has evolved over time from NFPA 70E to NESC Article 410, that's kind of the direction we're taking. And if we go to a couple steps further down in the OSHA documentation, tables 6 and 7 give you a range of voltages, fault currents, and then the maximum clearing time and cycles to hit each one of these calorie levels per square, these energy densities. And if you'll notice, they say, well, we did this by applying the ArcPro method listed in table 2. So bringing that all back down to the EasyPower application, we're saying we can come at the same way with the same type of methodology. And what I'm about to describe is actually documented in Practical Solutions to Arc Flash Calculations, which you can download from the website or request. It's actually a book, so you want to download it. It can't be emailed. And here's what I'm going to show. I have a series of buses based upon the voltage. So I'm showing here the 15,000 volt bus, and each of these utilities is set up to supply 5,000, 10,000, 15,000, and 20,000 amps. So let me jump into the tool and we'll do this. And this is kind of clever. And so what I've done, I don't know if you can see it, I've got all of these voltage ranges set up in the tool, and I just deactivate all but the one I want to look at. But in essence, what we're doing is we're setting up this utility for 25,000 volts and set up to supply 5,000 amps, and I'm using just a 5x over R to make it simple. So I'm going to go back and deactivate this so I can look at the results here. And what we've done, very much similar to what we did in the previous example, everything's set up as an open air bus, except in the arc flash hazard tab, I'm limiting the maximum time to 1 second. The benefit of that is we're essentially normalizing, since EasyPower doesn't show, even though we're calculating the heat flux density, what we actually show are the incident energy, and that's the result of the heat flux density times time. And so at 1 second, that will be the same units as you'll get from that chart that we were just looking at from OSHA. So with that said, I'm going to short circuit, go to my short circuit options, pick out open air buses, go to advanced. I'm above 15,000 volts, so we're going to apply 15,000, apply this, fault line to ground, and fault the buses. And so now you can see for, I think this was a 15,000 volt bus. Yep, 15,000 volts. These numbers should match what we got from the OSHA graph, OSHA table. So let's kind of look at this. Here's the table we got out of NESC, and I guess I'm looking at 15,000. So I should expect to see 4.9, which I do, 12.5, which I do, 22.2, which is there, and the last one is 34 calories per square centimeter. All right, so what this points out, and you can go through each one of these, and it's a nice exercise, frankly. That's why I encourage you to download that application and work through this. But it shows how we've literally came up with adjustments to the software that match exactly these matrix points, and that's what's used as we're applying that model along with the trip times in the tool to produce the instant energy, and they come very close to matching the same numbers that OSHA came up with in these tables that we were talking about. So that was a long-winded way of getting there, but essentially what we talked about is how to apply the model, where the basis of the model came from, how it complies with the standards and the requirements for the industry regulations, and it's all in one tool, and you can continue to use the same methodology that we've been using all along. So where does that leave us? Appreciate everyone for joining us today. We have on the website all the regional training locations and dates set for next year. I encourage you to check those out. If you have any questions about this or anything else regarding the use of the tools, you're welcome to contact tech support at easypower.com. And by all means, go to our, in fact, let me kind of show you how to do this. It's one of the advantages, I think, of having the tool from the database edit, go into the View Start page, and again, this is version 9.8. Go to the Arc Flash Center, and it brings up this web page, and the book I'm referring to is this newly updated Practical Solutions to Arc Flash Calculations, and download it, and you'll find the chapter on single line to ground applications. Okay, appreciate everybody is attending today, and we'll be talking to you probably in the new year. Have a good one.